Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everybody. It's my great pleasure to have Paris Smaragdis and Biksha Raj here from Mitsubishi Electric Research Labs. I've known Biksha for quite a while now, since I think 1998, when we shared an office at CMU, and I've known Paris for a while too, pretty much since Biksha got to Merle and started working with Paris. So we're sort of going to have a tag team presentation today, two parts of the same talk, first half by Paris and then by Biksha. So without further ado, here's Paris.
Thanks. So you've been staring at this slide for a long while, so no need to elaborate on the title. I'm Paris, as Mike said. So I'll be doing the first half of the talk. I'll mostly show interesting demos and stuff, get you more psyched about what we're doing, and then Biksha is going to tell you all the deeper stuff. So here's kind of an overview of the talk. I'm going to give you some motivation why we did this type of work and what's the reasons behind it. And then I'm going to talk about PLSA, which is a very interesting decomposition algorithm, and then show some two shift invariance versions for it. It's probably not clear to you right now what that means, but hopefully you'll get it by the end of the talk. So, motivation. A lot of the signals that at least I consider fun tend to be positive. So I'm an audio guy. I use a lot of audio spectra. They're always positive. Images also have a tendency to be positive valued. Text sometimes is positive. But when you usually take like a machine learning course or some pattern recognition course, the first thing you learn about is PCA, and then you might learn about ICA or other types of dimensionality reduction techniques where they can find some structure. And you don't usually see a constraint that the data is going to be positive. And the problem with that is that you end up having lots of weird artifacts because of that.
What do you mean text positive value is solid, right? How do you define?
Well, you have a bunch of character numbers, at least in my way of dealing with text. So here's an example which I think kind of describes this very well. So these are pictures from what's called eigenfaces. So it's a PCA analysis on a bunch of faces. It was groundbreaking work when it came out, and it's still very efficient when it comes to classifying and doing stuff like that. But there's a bit of a problem. This is what PCA is going to find as a structure in a face database. And even though it's great for classification, you can probably tell that these things don't really correspond to something that we will find interesting in a face. We have all these weird ghostly images. There are images that also assume negative values, which we're not sure how to actually translate to something meaningful. And it's not satisfying in a sense. So this is one of the things we're going to try to address. How do we deal with positive data? And the other thing is, what would happen if those faces were actually in the database were shifted left and right, up and down? In this example, you had somebody set people up, everything was aligned and nice. That's not always the case in the real world. So these are the two things we want to focus on. So our objective is going to be first to develop a nice transform where we don't really use cross cancellations to superimpose a bunch of bases and get something. We want to end up with components that are actually meaningful to us. And the second thing is we want to have shift invariance. When things move around, we want to automatically deal with that. We don't want to have to actually align everything by hand. Just a very brief overview of what people have done before. There's the principal and independent component analysis, and they're like very, very basic bread and butter stuff when it comes to machine learning. They're basically just a simple linear transform. You have this random vector x. You want to find some linear decomposition of it so that you get some properties in the output. And PCA wants to get orthogonal outputs. ICA wants to get independent outputs. Huge list of applications. People have used it for a lot of things, and they work very well. But again, they don't really deal with positive data. NMF was an algorithm that was introduced in '99, I think, by Li and Sung. And they sort of addressed this problem. What happens if you want to decompose something which is non-negative valued? And what they did is actually something that's very similar to PCA and ICA. They said, oh, we have this matrix over here, H. This matrix X, and we want to sort of decompose it as a product of two other matrices, but everything has to be non-negative. And when they did that, they found out that you can actually come up with some very, very interesting components. Things didn't end up being those weird ghostly images you saw in the faces. They actually ended up extracting eyes as one component and noses, and stuff like that. The learning rules that they used were extremely sexy because they were very efficient. They converge very fast. Unfortunately, nobody has a clue why they work. I'm not sure the authors do either, but oops, that's recorded. I shouldn't say that. But one big problem with this approach is that it's not really a probabilistic framework. If you want to take this thing and plug it into an HMM or plug it into in an SVM or something like that, you have no idea how to actually get probabilities out of it. And that has kind of turned people off when it came to NMF. So we're going to start, we're going to start the stuff that I'm going to talk about now from the probabilistic latent semantic analysis. That was an algorithm that was originally developed for text analysis by Hoffman back in 1999, and it's basically a probabilistic version of the SVD essentially. You want to find correlations between words or letters or whatever. People used to do SVDs for that. Hoffman did this in a probability space by using the PLSA. And what it does is actually very simple. You have a joint distribution P of x. You want to break this down into a sum of marginals. So you have a bunch of marginals on the x-axis. You have a bunch of marginals on the y-axis. You multiply them, you get these joint distributions. You want to have a bunch of those and add them together to approximate the distribution you want to model. And this is all, of course, conditional on a latent variable. The way that was introduced was in a 2D setting. It's pretty straightforward to actually come up with a multidimensional generalization. You basically have more marginals being multiplied. So no big deal there. Probably don't want to spend too much time on how you estimate those things. It's fairly straightforward EM training. You end up having a pretty simple E step, then somewhat simple M step. And the thing that I want to highlight here is that you can go through the EM derivation, and at the end you get to things which, with some algebraic manipulation, end up being the same as the NMF multiplicative rules. Yes?
It became PLSI, and the other one was PLSA.
Yes.
Is it a difference? Or?
I think Hoffman had two papers. In one of them it was called PLSI, and the other one PLSA. So it's probabilistic latent semantic indexing and then analysis. So if you're doing text stuff, you care about indexing. If you're just decomposing stuff, you call it analysis. So at least as far as I know, there's no difference. As far as I know, yeah. One interesting point here, which I'm sort of not going to elaborate at all, is that the whole NMF thing was actually a version of this. The non-negative matrix factorization. So it was the second transform I showed before.
So the one you're talking about is mathematically the same as...
It's numerically the exact same thing. Only this one, so in the matrix, on the non-negative matrix stuff, we were decomposing a matrix, so it was explicitly two-dimensional. In this case, our distribution that we model can be a multidimensional distribution. So you're essentially doing a non-negative tensor decomposition as opposed to a matrix. So it gives you much more flexibility and can actually derive likelihoods and stuff like that, which is always a good thing. Okay, so enough math. Here's an example now. So suppose I would start with this distribution here. So we have three Gaussians, one big fat Gaussian down here and two little thin ones over here. What happens if we do PLSA on that thing? So we're going to get, in this case, we wanted a decomposition in terms of three. We had the latent variable assumed three different values. So we would get three marginals on the x-axis, three marginals on the y-axis, and then three numbers which are the priors of each marginal set. So what we get here is that these are the marginals on the up-down axis. So you can see that the first marginal here pretty much describes the profile of this Gaussian, and then this equivalent profile here describes the marginal on this side, and likewise you can model the other two Gaussians as products of these guys here. And then you have the priors in the front of the decomposition that tell you how much of these Gaussians is present into the distribution. So if you basically multiply this together and weight them by this, you get the approximation, which is essentially the same thing. So we managed to describe this probability distribution in terms of a sum of marginals. So in that setting, it's not spectacularly amazing, right? I mean, it's a bunch of Gaussians. So let's see how we can actually use those in more real-life signals. So at the beginning, I'm going to show you some applications of PLSA just on audio. So simple stuff. So when people deal with audio and they want to do something complicated like recognition or something like that, usually they throw phase away and they work on magnitude spectra. And magnitude spectra are essentially some sort of a histogram. It tells you how many little time frequency atoms hit every point in the time frequency plane. It's like a wavelet counter if you want. So it's essentially a distribution. And we can model that using PLSA. And since it's a distribution, of course, it's positive. Everything works out fine. So I'm going to show you examples. I have two examples. One of how we can do separation of sources and object discovery, and then some denoising as well. So here's the simple case. So we have a nice little sound scene. Let me see if I can play that. Little trip back to the 80s. So it's a bunch of drums. This is the time frequency representation of that sound. It's in log scale, so it's more easy to see. So you can, if you kind of look at it, you can kind of identify different instruments in there. So we have the cowbell, which is this harmonic-looking thing over here. Then we have the claps or the snare drum, which is this big wideband thing here. We have the bass drum, which is all this energy down here. Those are sort of the sounds that we want to that make up the scene. Now, if we do a PLSA on that distribution, we end up getting some very interesting results. So on the marginals describing the frequency domain, we get stuff like something that's very peaky at the low end, which is essentially the bass drum. Or we get something that has all these harmonic peaks, which is essentially the little cowbell here. Or you get this wideband thing, which is the clapping or the snare drum. And the corresponding pair over here tells you how much that particular spectral profile is going to appear across time. So we can say that, okay, we have this wideband thing here, and it appears at this point and at this point. So we've essentially modeled this blob over here, which ends up corresponding to an instrument. And of course, if we know...
So you think this spectrogram as a matrix?
As a distribution.
Okay,
So it's a joint distribution of time and frequency.
Yeah, actually, for PLSA, I haven't actually followed the detailed method, but for LSA...
If it was LSA, it would have been a matrix.
The matrix.
Yes.
Okay, so when you do singular value decomposition,
Yeah.
you actually, most people just take out, the components that has...
If I were to do singular value decomposition, then these things would be the orthogonal bases on one side, and this would be the bases on the other side.
Okay.
But the SVD would screw things up because it would try to use cross-cancellation to describe everything. So instead of getting nice things which describe activity exactly the way I want it, you would get things that cancel out that would be orthogonal, which would be it's kind of a meaningless constraint when it comes to those things. It would describe the same energy in a sense, but it wouldn't give me the results I want. Things would be mixed up.
So my understanding about LSA versus PSA on text application, I feel that they're very similar to each other. People never claim that one works and the other one doesn't.
I haven't used it on the text space too much.
He came here to give a talk. When we asked him this question, he said, "Well,
Well, actually, in terms of functionality, yes, here what we are looking at is the semantics of, in an acoustic sense. Now, what do you mean by a negative power spectrum? There is no such thing as a negative power spectrum.
yeah, okay,
So if you just did LSA, then the bases that you would get, which are the building blocks, are going to have positive and negative components. And so if you thought of each of the bases as a sound, you're going to get a sound which has positive spectral energies and negative energies, which are totally meaningless.
okay."
And so, as a result, you're not going to get anything that actually
I see.
corresponds to something
Well, semantic, yeah.
physically meaningful.
So essentially what he's trying to say is, if you want to think of a generative model, PLSI is a generative model, LSA is not.
Okay, I see.
The function that you're optimizing in these two cases are different.
Okay.
LSI, you're trying to have a low-level representation which minimizes the Euclidean distance
I see.
of the
Okay.
representation versus the original data. Here it's the probability of generation. That's
I
the.
see. So you think about PLSA as a constraint LSA by making things positive?
No.
Not
That's
necessarily.
what you do. Okay.
So it's a
We'll
generative
get to
model.
that. I think I
Right.
mentioned.
There's a lot of stuff that's hidden under the rug right now, so I think Biksha is going to elaborate more on that. Yeah. So now we have a bunch of spectral profiles. We have a bunch of temporal profiles. We can basically combine them and actually extract just the sound that we want out of the mixture. So if we do that with one pair, we get this, which is I think is the bass drum. So we have this low energy thing, which describes bass drum, and then what's another one? This is going to be the hi-hat. So. And then we get the cowbell. And what else? Hand claps. So we've essentially managed to grab out of this mixture all the components that were present. Yes?
So then you assumed you know how many components are there in advance.
Yes. So
you
that's
didn't
like
know
the
you would
universal
know.
problem when it comes to dimensionality reduction, right? How many components do you extract?
Plus, I think, did you have to, how many times did you have to run it for you to get this kind of decomposition? Or does it produce the same? In my experience, PLSI produces different decompositions at different time. And sometimes you could end up having mixed models. I mean, sometimes it's, I work with it on text, for example.
Mm-hmm.
Very often I get mixed topics, which don't mean much anyway.
On text, you typically get all kinds of mixed stuff, and you have to work very hard, and you actually use your brains to make it to, you know, to figure
Well,
out.
the difference here is that
I don't know why audio
Yeah.
would be different, so that it, I mean,
you have a lot of data. You have a lot of data and very few correlations. So this is a huge amount of data compared to a text document, and you only have 5 or 6 things happening in there. So you have a lot of information pointing at the right direction. In text, you don't really have as much structure. And that's what makes a difference in this case. And in my experience, I mean, especially in this example, you always get the same answer. You might get a permutated answer, which doesn't change anything.
but it also depends on what kind of distributions you assume for P of F given Z and T given Z.
There's no distribution assumption.
So you just do a histogram. Okay.
Yes.
Okay.
But it looks a little bit like a wavelet, the way you represent it. But you still have the time and you got a basis.
Well, you know, short-term Fourier transform, wavelet, it's all kind of the same thing. You're just thinking in a different grid.
No. After you do this analysis, you still come up with this kind of basis and the weight.
Yes.
So it will be a special case of wavelet.
It's an extra level of decomposition on top of frequency decomposition. So this thing can actually be general, can be sort of extended to even more complicated stuff. Probably shouldn't spend too much time on that. But you can actually do that with do piano music transcription. Every piano note in a piece of music is going to have a different spectral profile. You can actually learn an entire piece of music. You kind of pretty much know how many notes there are. And then what you end up getting as the temporal weights is where each piano note was located. So here's an example of a Bach fugue. And well, I guess you can see the lines. What you see here is basically how much each note was active at any point in time. And you kind of have to take my word for it. It pretty much identifies all of the notes. Stop. So it pretty much identifies all of the notes. I think it only made like one mistake. And it offers a pretty nice decomposition of the entire music piece. Okay, so that was an example where we had unsupervised learning on spectra. I had a spectrum. I said, okay, give me that many components, and then that ended up being meaningful. And you're probably thinking right now, okay, if I start speaking or something, there's not one spectrum that describes my voice. Things change all the time. It's not such an easy thing. How do we deal with that? So in that case, we actually have to move to a supervised strategy. What we can do now is we can actually learn the spectra that describe a particular type of sound. And then when we encounter that sound in a mixture or in some other situation, we can actually see how much those spectra exist in that mixture. And that's great for denoising or extracting speech out of stuff. So here's an example. So let's focus on this spectrogram over here. So this is I think a male speaker, and he has some sort of chimes playing in the background. Let me play you the sound as well so you get an idea of that.
The morning dew on the spiderweb glistened in the sun.
Okay, pretty noisy. So you might notice that if you sort of look at things on the frequency axis, the chimes have a pretty specific spectral pattern, right? They don't really interfere so much with the speaker. They don't sort of move in the same frequency space. The speaker on the other side tends to have a lot of energy down here. He doesn't have all these straight lines going through. Spectrally, they're very different sounds. So if we online have a model where we trained on how chimes sound like, and sort of keep a database of that, of their marginal distributions on the frequency axis, and do the same thing for the speaker, once we have a mixture of those two sounds, we can try to analyze it based on those marginals and then see which one exists where. And then we can do a reconstruction where we say, let's try to reconstruct the entire thing where we don't really synthesize with the chimes in there. We're just going to use the speaker, or we're only going to use the chime frequencies. So here's a couple of examples. This is an example where we have a a female speaker with city noise.
Jane may earn more money by working hard.
So it's pretty noisy. Offline, we've learned a model for that female speaker. We also have a model for the noise. If we do a reconstruction where we only use the frequency distributions for the female speaker, we get this.
Jane may earn more money by working hard.
And I don't know why you would want to do that, but you can also get the noise as well. And here's the example with the chimes as well, if it plays.
The morning dew on the spiderweb glistened in the sun.
So that's the mixture.
The morning dew on the spiderweb glistened in the sun.
Now one thing that, yeah.
I see how you can learn a model of, say, the chimes with the model they presented, but how do you learn the voice of the person? It's not like the voice has fixed patterns and, you either say eh or you, etc. I mean, that may be a very, very big model.
So yeah, for this one I think I used about 80 distributions to model the speaker. So the assumption is that whenever I say ah, it pretty much sounds the same all the time. And every word I say that uses the phoneme ah, it's probably going to use the same distribution. And that's going to be sufficiently different from the noise sources. And that's what the assumption is right now. And
I'm trying to understand, since PLSA is a generative model, and what part of mathematics over here that actually
That I can
represent?
cover some of
You
that.
cover that, okay.
and
I'm confused about your method here. Are you using this, the pre-mixed audio recording of him saying that to build your model for his speech?
I have different recordings of the chimes and that speaker. And then once I have a mixture, I try to explain that mixture using the spectral distributions of those two sources.
Oh, cool. So you are using
training and test is
separate.
Yes, I'm not using the same
Okay.
sounds. And of course, as a side note, if I have the same speaker mixed with himself, there's no way you can separate that because they have the same frequency profile.
So have you tried with a generic speech model? I mean, trained with several different speakers instead of only that speaker?
No. Not that I remember. No, I don't think so. I think Biksha has done more speech stuff with that, so you can agree with him on that. Here's a more extreme denoising example. This is of a recording, it's a soprano and a piano. I'll play the sound in a moment. And this is a slightly different situation because now we can't really get the soprano distributions anywhere because she's always singing with the piano. We only have a few snippets of in the piece where the piano is playing by itself. So we can learn the distribution of the piano, but we can't really learn the distributions of the soprano. So that's a slightly different methodology here in that we learn about a bunch of distributions for the piano, and then we try to explain the mixture with the piano distributions plus some unknown ones. And the unknown ones actually end up tuning into the soprano because that's a lot of the unexplained signal. And then the methodology from that is pretty much the same. So this is these are the extracted spectrograms. Let me play you the sounds as well. This is the mixture. And of course, a problem with that is that when you do music, you actually try to synchronize a lot of your harmonic content with the other instruments. So it's not as simple as having like noise and speech. It's slightly more hard. So that's the extracted piano and voice. So you can kind of hear the piano notes that coincide with the soprano, but the rest is kind of filtered out because it doesn't really have much relationship. Yes?
Here's where everything fades out.
Yes, so at the end so over here, the piano is not extracted very well. And the reason for that is that the soprano starts having this wild vibrato here, and she starts covering this huge...
No, in between the notes.
In between the notes?
Yeah. And it goes silent for like a little while.
That's because the piano starts dominating that part, and it starts stealing a lot of energy from the soprano. And again, a lot of those things are not very easy to understand why they work that way. So that happened to be the best approximation in this case. Okay, so I've talked about audio a lot right now, and of course one thing we all know is that audio has a lot of time structure. Yes?
I'm still not clear. When you say best approximation, in what sense?
So we have a distribution which is the spectrogram of the mixture, and we're trying to approximate that using the marginals on the frequency axis that we have learned before offline. So we want to find which are the marginals on the time axis that would best describe that mixture given the knowledge on the frequency domain that we have.
You said that it carries some perceptual sense, right?
Well, the results end up being perceptually interesting as opposed to what you would get using an SVD, for example. I can't claim that this is how the brain works or anything like that. But if you do PCA on a spectrogram and actually hear the results, what you're going to get is something like, which mathematically might be beautiful, but it doesn't make much sense. And I guess that's the point I'm trying to make. Yeah.
You're assuming that the spectrograms are additive, right?
Yes. Yeah.
That isn't always true. Do you think that there's anything to be done there, or is it causing any problems for you?
Yes, that is a very strong assumption I'm making. On average, that's an okay assumption. It seems to work fine. People have shown that even if you start masking things in and out and sort of have a binary mask that you impose, you can still get something that sounds good. So even if you don't believe additivity, you can at least believe that you have some exclusivity on a particular time frequency spot. We tried thinking of ways of dealing with that. You can actually start raising things to powers where things might become a little better or not. We haven't played too much with it, at least in terms of results. We've been thinking about it, but it doesn't seem to be a big stumbling block at the moment. It definitely becomes a problem when you have something like 20 sources added together, because then you actually start having a lot of cross cancellations. But then again, if you add two sounds together, things are going to get canceled out anyway, and you can't really model that. You can't make up information.
I'm missing something important here. So you have a generative model. Mm-hmm. How do you synthesize once you get the generative model? Because I don't see how you get the relative strengths of the sounds at different levels. Do you have to take that out of the equation and put it back in later?
So in the M step of the EM training, I had an update rule for the marginals on one side and then a learning rule for the marginals on the other side. What I do is I assume that I already know the marginals on the frequency axis and only train on the marginals on the time axis. And I think, yeah, the speaker is going to go to that. But I'm basically clamping the frequency domain stuff as it is and trying to see what's the best time distributions to model what I have.
You use the original phase from the composition.
And I'm using the original phase to make an audible decomposition. So audio has a lot of time structures. It would be really nice if we could model little snippets of sound as opposed to just modeling a single spectrum. Like I said before, when I speak, I don't have like this 5 different spectrums I use all the time. I actually have little phonetic structures I use all the time. And it would be really nice if I could model that. So the extension to that is pretty straightforward. That's the ugly equation for those who like integrals. That's the more elegant one. Essentially what we're going to do now is we're going to say we still have a summation of a bunch of products, but the products are going to be convolutions. So I'm going to have what we call a kernel distribution, which can be an entire patch of a distribution, and that's going to be convolved with what I call an impulse distribution, and that's going to position that left and right where I want it. If this convolution, if the length of the kernel was going to be 1, then essentially this gets demoted to a straightforward PLSA. Best way to describe this is, I think, to give you the little Gaussian example. So imagine that we have this distribution over here. If you look at it long enough, you'll notice that we have one Gaussian looking at the top right, which repeats 3 times here and then once more over here. And then we have 2 other Gaussians which form a little wedge, and they repeat once here and once here. So we have the same distribution, gets repeated on the left-right axis in some random way. If we do this type of analysis, we're essentially going to try to find a bunch of kernels that duplicate on this axis. And if we train the way with a convolutive PLSA, we can get a kernel which looks like this, which is actually the one repeating component, the other one looking like this. And then the impulse distribution is going to describe how these kernels are going to be placed on the left-right axis. So the interpretation here is that we have the wedge here, it appears once, then there's a pause, then it appears twice, which is the case here. And then we have the single Gaussian. It appears 3 times in a row, then small pause, then once again. So it's 3 times in a row, pause once again. So now we've modeled some of the shift invariants on the left-right axis in the probability distribution space. Does that make sense? Maybe.
Quite different from the previous one because you now one of your objects is not something that's one line
Exactly.
at a time.
Yes.
It's something that's extended into.
Yes. So now we've kind of extended the idea of using multiplication of marginals to using a convolution of distribution and a series of impulses.
Earlier what we were saying is you have this one slice and it can occur anywhere. Now you say you have this patch and it can occur anywhere. Essentially it's the same thing. You just taken your bases and stretch them out in time. Okay.
It'll start making more sense when I go to images and stuff like that. Boring math, it works out. Don't worry about it. Like I said, we're going to learn patches of distributions. So that's useful in audio because we have things that often repeat in time as entire segments, as little snippets of sounds. Same thing for images. If you have things that shift left and right, like characters, it also works well. So here's a more pictorial example. When you have an image, you can always think of it as a distribution as well. You have the probability that a photon hits a particular XY spot, right? So here's an example of some characters. I have no idea what this says. I hope it's not offending. So we have a bunch of characters. We assume that this is a distribution. And if your eyes are sharp enough, you can probably notice that this character gets repeated once here, this guy gets repeated over here, and then this one just happens by itself. If we try to analyze this distribution using the regular PLSA model, we would have to model it as a summation of marginals. And there's no way in hell that those things could be approximated by a couple of marginals. They're very complicated shapes. If we do the convolutive case, we can ask for something about that wide that appears on the left-right axis. And if we do that, we end up extracting 3 bases, which are these 3, which are actually, whoops, well, I plotted that in reverse, so, okay, pretend that's reversed. So these are the characters over here. And then we're going to get the impulse distributions, which are going to tell us how those things are positioned. So if we take this character over here, it only gets a spike in the middle because it only appears here. If we take this character, it has a spike at the beginning because it's the first one, and then one at the end because it's also the last one. So now we've modeled a fairly complex distribution, if you like, and managed to deal with shifting left and right. Slightly more realistic or real-world scenario is this recording. 1, 1, 2, 1, 2, 1. So that's me saying 1 and then saying 2 on top of that. So if you contrast that with the case before, it's the same speaker, I pretty much have the same spectral profile. But I do have this bunch of repeating snippets of sound that are shifted in time. If we do a PLSA analysis on that, we're going to get a spectrum for 2 components. We're going to get a spectrum for every word, if you like, and we get crappy results like this. But if we actually try to find an entire patch of a distribution that repeats in time, we get more interesting stuff. 1, 1, 1, 1, 2, 2, 2, 2. 2 seems to like the noise as well. So I hope this kind of makes sense of the convolutive operation. We have this thing which repeats over time a lot and can now find out where it appears. Yes?
Clarify. Do you know how many figures are there, like unique figures? Or?
I would have, yeah. So this is equivalent. I need to know the dimensionality of my problem.
Like in the character example.
In that one, I specifically asked for 3 characters. Yes?
There might be different combinations. Doesn't have to be these 3.
I could have asked for 18 characters, and then you would actually start getting elements that get repeated. And that sort of goes back to finding the proper sort of dimension for your problem, which, as far as I know, nobody has solved effectively. It's kind of like finding the dimensionality when you have a PCA problem. You know, what's the right one? Nobody knows. It really depends on your problem.
So there, the word 1 was repeated, or was it said twice by you?
It was said. I turned on the microphone and said 1, 1, 1, 1, and then said twice, 2, 2, 2 on top of that.
So
it wasn't. Yes, it wasn't identical. It was different. So we looked at very large-scale sort of objects right now. You know, a word is a pretty significant chunk of time, at least for speech. What happens when we start thinning down that kernel window and start looking at smaller things? Then we start getting very interesting stuff. So these are the extracted kernels from just analysis of some timid speech. And what we start seeing here is that we start seeing some harmonic structure. We're seeing some maybe consonants over here. We see little snippets of sound that actually describe a lot of the speech structure. And what's very interesting in that is that it changes depending on the speaker. So these are a bunch of kernels we extracted from a female speaker. And you can see the harmonic structure here. You maybe have some consonants, which are all the noisy patches over there. Now, if you contrast that with a male speaker, you'll see that it's different. The male speaker has a lower fundamental frequency. The harmonics are more clustered together. The female has a higher fundamental frequency. Things are going to be more spread out. And now the interesting part is that if I analyze a mixture of male and female speech, I get some of both. So I get some, like this here belongs to the male speaker, low frequency, clustered harmonics. This one belongs to the female speaker. So we kind of have, and Biksha is going to elaborate more on that, but we kind of have like an interesting insight on how we could construct a scene where two known speakers are speaking at the same time. It's constructed out of little patches from the two speakers. And if we sort of act on that assumption, we can say, okay, let's learn something about one speaker, find out its phonemes, learn something about the second speaker and the phonemes of that speaker. And then if we have a mixture of those two speakers, let's try to explain that scene using the kernels I've learned from both speakers and see how, and then try to do a reconstruction using only the kernels from a single speaker. And if you do that, you actually get interesting results. So this is one of the better sounding examples.
Jane may earn more money by working hard.
So I've trained offline on those two speakers speaking different sentences. So this is the reconstruction using only the female kernels.
Jane may earn more money by working hard.
And the male reconstruction.
Don't ask me to carry an oily rag like that.
Now, if I had the same speaker speaking on himself, obviously this wouldn't work because all the kernels would describe pretty much all the energy. So the more different speakers are, the better. And this is a case where you had a very sort of resonant male voice, and then the female was very damp, high-frequency speaker. If you have two male speakers, it's not going to sound as good, for example.
So how many kernels you have per speaker?
For this one, it was probably 40 or 80 or something. You don't want to use too many kernels because then you end up describing too much detail, which means that you can actually describe a lot of other speakers as well. So there's always that sweet spot, which I don't have a nice analytic way of finding out.
So when you were saying 1 and 2, and they were mixed earlier, you could separate them much better than here. I presume that's because there was repetitive. You were saying 1 over and over again, and that's the main difference.
That was a cleaner case because it was an unsupervised case, and I was trying to find the structure in that particular distribution. In this case, I'm trying to explain the mixture using prior knowledge from other recordings. So I actually had to fit my frequency, my little kernels, into the mixture. So things are not going to fit that well.
It's clustering on the training data itself. This is extrapolating from some training data to test data, which is always harder.
So what is the duration of the kernels?
I think it was 8 time slices. Each time slice, I think, was 512 point FFT. And the sampling rate was about 16K.
And the reconstruction is just a concatenation?
And the reconstruction is basically, I'm trying to reconstruct the scene using only the kernels of every speaker and then using the original phase of the mixture. So I'm modulating the phase of the mixture using the amplitude.
The reconstruction is not just concatenation, it's the whole convolutive model.
Yeah, it's not just one after the other. They're basically all mixed together according to what my fitting weights were. Okay, so if you do images, it's kind of obvious right now what's coming next. We want to do two-dimensional stuff. So you just add another t, and everything still works out the same. Blah, blah, blah math, no need for that. There's a minor complication when you start moving to the 2D case. which is it's not clear what becomes an impulse and what becomes a kernel. So if you sort of think back in the character example, I said I have these little patches that replicate left and right. If those had enough freedom to replicate up and down as well, I would basically be convolving to images. Now, which one would end up being the character and which one would end up being the little impulse? It's not something that's predefined. It could be either one. So we need to find a way where we can ensure that the training is going to give us a lot of stuff or a lot of energy on the kernels and as little energy as we can on the impulse distributions. The proper way to do it is to ask for a very very high entropy, very low entropy. On the impulse distribution, the math gets very hairy. We've done it. We're doing it, actually. The easy way around it is to just add a little step in the EM training and just basically raise into a power less than 1, raise the kernels into a power less than 1. That's going to force them to be more flat, have much more energy, and they eventually end up sucking up a lot of the energy and leaving the impulses as the impulse distribution as having more impulses. And then you can start having that power tending towards 1 as you finish training, so things are clean. Again, Gaussian example, simple stuff. We'll start with this input distribution. There's basically 2 different types of Gaussians looking in different ways, discarded all over. If we do the analysis, we end up getting these 2 kernels, and then these are the impulse distributions that describe where those things should have been placed. We can move to a slightly more complicated example where we have this handwriting over here. Again, we can do the same thing. We can ask for kernels about that size, and if we do that, these end up being the kernel distributions, obviously correspond to the letters here. And then I don't know if you can see that very clearly. These are the impulse distributions. You basically have little dots that describe where each letter was present. And a nice side effect of that is that it makes my handwriting look more uniform. We can talk about 3D convolution. You can have x, y, and then have an extra dimension, which is going to be your RGB, and start shifting things there as well. So this is the original input, a bunch of heads. If we did the analysis and looked for one component, then it actually ends up being a nice color face and a very spooky reconstruction of that. And then we get lots of energy where each face was located. So you can actually apply this into all sorts of dimensionalities, and it's usually fine. If you are into DSP, this kind of starts tending into positive deconvolution, which is one of those problems that has many solutions, but nobody has come up with a good solution yet, to my knowledge. What we're trying to do is figure out, if you know that you have something positive that gets repeated over time, if you do a regular deconvolution, you're going to end up having negative stuff in there. The Fourier transforms are going to do, the convolution operator is going to do that for you, which is pretty bad. So you can actually use the same technique where you fix the kernel or the impulse depending on what you have and do deconvolution and actually estimate positive only components. Probably not for you, but astronomers actually love that kind of stuff because they usually have this convolution happening on the stars and things like that. Let me see, I think I'll skip some stuff and go into Biksha. So I've talked about 3 different cases of PLSA, the regular one that was known, and then showed some extensions on the 1D convolution and then multiple dimension convolution and then sort of some of the complications that arrive. So the message that I want to leave you with is that non-negative decompositions are useful because they come up with things which are much more interesting than a straightforward SPD or ICA or something like that. And the other good thing is that now we have a nice statistical framework to deal with when it comes to non-negative decompositions, which we didn't have before. So you can start doing all sorts of fancy stuff like stuffing this thing into an HMM, so you don't have to deal with factorial HMMs because they're going to be additive HMMs and stuff like that. So thanks from me, and then Biksha is going to take over and do what it does. And questions, yeah?
So when you are making the impulse response and the kernel distribution, so how do you initialize them? Or just try to
random numbers
arbitrarily?
They're just initialized randomly. Yeah, there's nothing special about it. One thing that I didn't mention is that you also have to specify the size of the kernel distribution. So before you had to specify the dimensionality of the problem, now you also have to specify how big you want the kernel to be as well.
If you have image, you have the image kernel, you have to say the kernel.
Yeah, like in the face example, I asked for
So you made this comment about putting a constraint on the entropy of the impulse or
yes.
so on where you want to go. That it's different, that is hard, but you exponentiate it. But there's some work that shows that exponentiating on the end step is essentially equivalent to putting an entropy constraint on the distribution you're after.
We actually have a more explicit way of doing the same thing. This is just a first step, and there's a more rigorous way of actually handling the entropy itself. And I'll mention that towards the end of my talk. So, but I'm not exactly picking up where Paris left off. I will actually step a big step backward and presenting everything from a somewhat different perspective. Hopefully this makes things a little clearer. My slides will be somewhat heavy on metaphor, a little thinner on results, and hopefully some interesting ideas. We'll begin with the idea of a multinomial distribution. We all know what a multinomial distribution is. If you have a pot with lots of colored balls in it, and if someone were to draw balls from this urn, then the probability you're going to only get the balls that you pick out are only going to have a limited number of colors, namely the colors that were already in the urn. And the probability of picking a ball of a particular color only depends on the fraction of balls in the urn that were of that color. It's a common enough thing. We've learned about this in high school. Now let's look at a power spectrum. If you compute the spectrum of a signal using a discrete Fourier transform, you're only going to have a finite number of frequencies in the spectrum. And what the power spectrum actually has is, along the x-axis, it has the entire set of frequencies. And do we have a laser? I don't know what this is.
The top button is the laser. The other way.
Okay. So you have, along the x-axis, you have the frequencies. Along the y-axis, you have the energy. And you can actually visualize this as a histogram. Thank you. Beautiful. So much nicer, isn't it?
Don't move it too long, it will burn the screen.
So anyway, it's nice to point with this. I think it's the x-axis. You can think of the x-axis as representing discrete events that could happen. And you can think of the y-axis, the energy, as the number of times this event occurred. So, speaking of it in ball and urn terms, you can think of an urn which contains balls. And every ball has a frequency marked on it. And the person, in generating a spectrum, simply draws balls from this urn and then plots a histogram of what happened. And this would be the model for our spectrum. And this is the entire procedure for generating a spectrum of a signal. Now here's a slightly more complicated model for generating a spectrum. The person doesn't have just one urn. He has many urns. And each of the urns has balls with frequencies marked on them, except the distribution of frequencies in any two urns is different. And now to generate a spectrum, what the person does is first he selects an urn, and then he selects a ball from the urn, notes the frequency, and eventually plots a histogram. If this is all he does, then really there's no difference between this model here and this model here, because you can simply sort of munge all of these urns into one single pot, and you'd get the same spectrum. But where things get interesting is when we look at how the person actually generates an entire spectrogram. Now, according to our model, the person has a number of pots, urns, with frequency marked balls in them. And in each time analysis frame, now, before we begin, what exactly is a spectrogram? We know it's time along the x-axis, frequency along the y-axis, and every vertical slice over here actually represents one frequency, one spectrum, which has been computed from one analysis frame. The color represents the height of the spectrum, of course. So according to this model, within each analysis window, what the person does is to draw a number of balls from the urns and plot the histogram. The point is the urns stay the same for all analysis frames. He doesn't change the set of urns from analysis frame to analysis frame. The only thing he changes is the manner in which he selects the urns to draw balls. And so the difference between the spectra at different time instances is entirely explained by
the relative frequency, differences in the relative frequency with which he selects the urns. Now, the first example I showed was of a simple multinomial. The second example is a mixture multinomial. And in fact, multinomials and mixture multinomials are the same distribution. In a multinomial, you would have a single probability term for generating a particular outcome. In a mixture multinomial, the probability of a particular outcome is going to be an integral of the manner in which you're going to select the particular multinomial and the multinomial dependent probability of that outcome. You just add these two up. And if you covered the process up with a big black box and just thought of it as someone sticking their hand into a box and pulling out numbers, then it wouldn't matter whether there was one pot inside or 20 pots inside. As far as you are concerned, it's just a multinomial. With one critical difference, that the mixture multinomial is very constrained. Now, if you have, say, 3 pots that you're going to mix to generate a particular multinomial, each pot has a number of possible outcomes, which you can think of, each of which has a frequent probability. So you could string these probabilities out into a vector and think of a probability vector. And this probability vector resides in some probability space. Now, if all the 3 urns, if all of your urns are independent, then the probability vectors would form the corners of a simplex. So if you have only three urns, the probability vectors for the 3 urns will form a triangle. And any mixture multinomial that you generate by combining these 3 probability distributions is also a probability vector, and it's guaranteed to lie within the simplex. And this is the constraint on a mixture multinomial. So when our Matt Picker draws a spectrogram by drawing numbers from mixtures from combinations of parts, what he really does is that for each analysis window, he generates one spot from within the simplex which is completely identified by all the urns that he has, where each corner represents one of the urns. And in generating the entire spectrogram, all he is doing is sort of generating a whole sequence of spots through this simplex. Now we have the model, but how exactly would we estimate the model? We have a mixture multinomial model for every frame. We know that the basic multinomial components do not change from frame to frame, but the mixture weights by which these multinomials are combined change from frame to frame, and all we have observed are the final outcomes, the counts of the various outcomes. Remember, we are thinking of the spectrum as a histogram of counts over a discrete random variable. And well, it turns out you can do this very simply. You can simply use the expectation maximization algorithm. All of us are familiar with it. If you sit down with a pen and paper, I'm sure all of you could derive it. The graphical equivalent for the model is you have a first level process which selects an urn, a second level process which selects a frequency from the urn. So this is the overall probability distribution, the model for a spectrum. Note that this is the probability distribution that's supposed to have generated a specific spectrum at the teeth analysis frame. This is a combination of the probability distributions for the individual urns. This is not a function of time. This stays constant. And they are mixed by these mixture weights, which are the only things that change from analysis frame to analysis frame. Given this, you can come up with a set of simple update equations which are extremely simple to implement, and I don't need to go through them, but you can check them up on the slides. If you just implement these formulae, you will actually estimate the distributions for the urns and the mixture weight in every single analysis frame. Now, let's put this model to work. Here are some examples. Paris has shown you one example already. Speaker separation. He's actually shown you multiple examples. I'll expand on some of those and show a couple of others. Bandwidth expansion. Single channel speaker separation, which you can do in different ways. You can also incorporate prior knowledge into the whole process, something Paris has not mentioned yet. And this is something, sparse representations is something he's already alluded to, and I'll explain it a little more. Consider the problem of bandwidth expansion. Now, as I speak to you over here, I am actually generating a lot of frequencies. I'm generating frequencies from 0 hertz all the way to about 120 kilohertz. You can hear everything between, say, 50 hertz and 15 kilohertz. And the reason my voice sounds the way it does is because you hear this really wide range of frequencies. But when you pick up a telephone, you're only going to get frequencies in the range 300 hertz to about 3.5 kilohertz. And the and the problem of bandwidth expansion is, given that you only observed this specific set of frequencies, can you figure out what the energies were in the other frequencies? We can look at this from the ball and urn perspective. Let's say that we know the exact distribution of all frequencies and all the urns that the speaker uses to generate a spectrum. And within each urn, he's got all frequencies, all the way from 20 hertz to 15 kilohertz, everything that we're interested in. And let's assume we also know the relative frequencies with which he picks the urns to select the balls to generate your spectrum. So in other words, we know everything about this mixture multinomial process that actually generates the spectrum. Given this, say we are only allowed to see the histogram at some subset of frequencies in the spectrum. How can we guess what the histogram was at other points? Now, you can sort of get an idea of this from this very simplified example. Let's say you had a pot which had only 3 red and 4 blue balls. And then someone drew balls from this pot an unknown number of times. And you were informed that in this process, this person has drawn exactly 3 red balls. Then what is your best guess for the number of blue balls that were drawn from the pot? It's easy enough to figure. But you can actually do it more rigorously, mathematically. I'm switching metaphors here, but that's only for this one slide. Say, think of a coin toss with a fair coin. Now, the probability of generating, say, m heads and n tosses would be given by this combinatorial formula. And so suppose I told you that someone has tossed a fair coin, say 100 times. No, I don't tell you how many times he has tossed it, but I tell you that someone has tossed a coin a certain number of times. And in this experiment, he came up with 25 heads. Then what is your best guess for the total number of tosses? And if you wanted a nice maximum likelihood solution, you would actually stick the number 25 over here and compute this term for various values of n. And the value of n at which it peaks is your best guess for the total number of tosses. And then once you have your best guess for the total number of tosses, you can go one step back and actually figure out how many tails he tossed. Easy enough if all you have are heads and tails. But if you have 10 possible outcomes or 100 possible outcomes, as you would in a spectrum, then this becomes a little more complicated to compute. But you can take a simpler solution which is not exactly the same as the maximum likelihood solution. Say you know that the probability of heads is p heads here, and you know that he has got m heads in the toss. Then you can estimate the total number of tosses by just inverting this. So say, for example, if I told you that it was a fair coin and that the person has tossed 25 heads, then it's easy, it's natural to assume that your best guess for the total number of tosses is 50, because heads occur half the time. And if you had 50 tosses and you have 25 heads, then clearly you must have had 25 tails. Simply, given the entire mixture multinomial distribution for a spectrum, now you can use the exact same arithmetic to compute what the histogram value was at all other frequencies given just some of these frequencies. The problem is you won't have all of it. So the solution we will use to expand the bandwidth of a narrowband solution is this. From some training data for the speaker, we will actually learn the urns, the component multinomial distributions for the speaker. Then when you get some narrowband data, within each analysis frame, you're going to estimate how he mixed those urns to come up with the final histogram for the spectrum. And then having done that, and then knowing exactly what the spectrum was and the frequencies that you have observed, you would compute the frequencies at the spectrogram at other frequencies. Now, in order to compute the mixture weights for the urns at each analysis frame, you have to ignore the frequencies you did not see, because in the narrowband signal, you're only going to be looking at a narrowband signal, and based on the narrowband signal, you have to sort of estimate how he combined the various urns. And the urns themselves contain all frequencies. So you would have to ignore everything that you don't see. The mathematics again for this, very simple as before. These are exactly the same equations we had earlier, with one small difference, that you're only going to be integrating things over the observed frequencies. Now once you've actually computed the entire process, the multinomial distribution, you have the urns, you have the mixture weights, you have the multinomial, you have the band limited signal, so you can take the whole thing back and compute the entire spectrum for the signal. So here's an example. In this example here, this is a full band signal that I began with.
The plan raised a question in some minds as to why the union didn't propose to acquire all of UAL and then sell the unrelated airline assets.
And I threw everything about slightly below 4 kilohertz out of the signal. And based on, and when you do that, this is what it sounds like.
The plan raised a question in some minds as to why
Clearly
the union didn't propose to acquire all of UAL
and now based
then
on what
sell
you
the
see in the lower
unrelated
bands over
airline
here,
assets.
I have actually reconstructed or computed my best guess for the upper bands. And when you do that, this is the spectrogram you get. You can see it actually does a pretty good job of even capturing things like fricatives. Even fricatives which really don't have a lot of energy in the lower frequencies. And if you listen to it, it actually sounds quite good.
The plan raised a question in some minds as to why the union didn't propose to acquire all of UAL and then sell the unrelated airline assets.
It sounds almost identical.
The plan raised a question in some minds as to why the union didn't propose to acquire all of UAL and then sell the unrelated airline assets.
So the correlation between upper band versus lower band is captured during the training of the mixture weight.
From the multinomial distribution.
No, but your multinomial distribution has a very limited number of parameters, right? So that probability will have, for
each multinomial is going to have the probability for each frequency.
I think the trick here is the weight.
The mixture weights, yes.
And the mixture weight has to be done in a time-dependent manner.
Yeah, and yes, and here and right.
How I missed your earlier EM for training the weight. If the mixture weight is fixed, like it's mixture, or Gaussian, then it's much easier to do it. But
no, because you just think of this as having lots of mixture multinomials, where the basic multinomials themselves are shared. The components are shared parameters. The mixture weights are not. So it's a very simple, very straightforward expectation maximization algorithm. There's nothing to it.
So the mixture rate at time t doesn't actually depend on at time the mixture rate at t-1?
No, it doesn't. Except whatever relation, except through this a posteriori, which depends on the globally tied multinomial components.
In this case, the mixture weight in the model itself is not a function of time. Right?
The mixture weight is a function of time. The multinomial is not a function of time. So here it is. It's got a CT to it.
Okay,
so think of it. It's a function of the observed data.
It's not a function of
so it's
time.
It's not a function of time. Within each it changes from analysis frame to analysis frame.
But it's not intrinsic model parameter.
No.
The intrinsic model parameter, you still have the mixture fixed.
It's just
which is a function.
It's the multinomials, which are constant. Yash?
You were motivating this in terms of telephone speech.
Yes.
In telephone speech, you don't have the nice marginalization properties you have with that.
You're going to have some additional channel effects.
You're going to have channel effects. You're going to have noise. Do you have a plan for dealing with that?
Well,
that's the preferred method of dealing with the actual nastiness that comes with the telephone signal that you don't get with this brick wall filter.
So I am being quite naive and simplistic in this particular example, yes. But in terms of channel effects are not such a serious issue so long as you can effectively model them as something that occurs as a linear filter that occurs within one analysis frame. Although I don't have the figure on this on my slides, it turns out that if you think of the graphical model for the whole process, then currently you have something that all that happens is that you end up having an additional component which completely bypasses the process, the urns. So it's a multiplicative component. So right now what happens is you have the first step which selects the urn and selects the frequency. That number could be multiplied by a second step which completely bypasses the urn and multiplies the frequencies regardless of which urn the frequency was drawn from. And it's just a standard, you can use straight up belief propagation to actually estimate that.
Okay, and it doesn't complicate the inference?
Of course it would. Every time you add an additional arrow, it does complicate the inference.
But it's not looping still, right?
Pardon me?
It's still nice. You don't need approximate inference. You can do it.
You should, because it's directed, highly directed. Yes.
And we're talking about reconstruction just the upper part, nothing below 300 hertz.
I could. I mean, I have not, in this example, I don't, the process is the same. I am not really, I have an urn, I've computed a histogram, and of which I've seen only some portion. What is my best guess for everything else I have not seen? That's all I'm using.
The same, how do you generate the face? The face is missing.
In this example, okay, here, this is kind of cute. Here I actually did some, I computed a linear transformation between the phase for the upper frequencies and the lower frequencies. It turns out you can do it in many different ways, and they all sound alike. Yes. I have not done, okay, you have a point over there. You have a very valid point.
Because humans, you use the envelope, the energy envelope above 2000 hertz, but below, let's say 600 hertz, we need the phase.
Absolutely, and that is something I have not addressed for the lower frequencies, no.
So you have a model from that speaker for this
yes, this is very speaker specific in this example.
So what if you have a control over the band you are selecting? So do you have any analysis of which band is more, which would give more compression?
I'm not. You're right, but I'm just looking at this blindly as a multinomial process, in which case, it has its drawbacks, and I think look at things like that. For example, it's questionable whether I can infer a lot about the lower frequencies based if all I had were the upper frequencies. And this is because if you actually looked at the spectrum of any particular basis, right, any particular multinomial, it's going to have very low, all the high frequency terms are going to have low probabilities, and the low frequency terms are going to have high probabilities. And it's hard to infer high probability events based on low probability events, although vice versa it's not so hard. So I cannot say.
How accurate are you in choosing each urn at each time instant?
I don't know, because this is all out, there's no ground truth.
Well, I mean, if you choose the wrong urn, you will have a wrong reconstruction.
Yes, but what exactly is the right urn or the wrong urn? There's no ground truth. You're right, but then I have no way of measuring it.
So for female speech, it's likely that fricatives are totally absent in the whole frequency.
Correct. Correct. And the hope is that if you yes, but the hope is that if you pull things out, the fact that there is a hole over here might actually correlate to the fact that there's something up there.
Or silence.
Or silence. You are absolutely right. So, and that's where now what I have not mentioned here is the convolutive version of it. Here I am speaking of every time slice independently, and whereas the convolutive version you're actually looking at patches. If you looked at patches, then you're actually going to capture little bits of transition information, which are supposed to be able to get you some of that information. In fact, in our examples, you get much better reconstruction with transition information and an additional factor that I will mention towards the end of the talk. Now, the second problem, single channel speaker separation. Paris has mentioned this, but to reiterate, you have two people. In my example, I'm using two people speaking simultaneously into one microphone, and the goal is to selectively separate out the signal for a target speaker from the mixture, or at least to enhance the signal for that speaker. Now, I must warn you that the examples I show are not going to be as dramatic and as beautiful as the examples Paris showed, not because I have purposely chosen bad examples, nor because I've purposely chosen good examples, but because that's the average example. That's how things come out. The model, now if I have two speakers, according to our model, what would I have? I have speaker 1 with his own set of urns, and he just draws balls from these urns at random within each analysis frame and computes a histogram. I have speaker 2 also with his own set of urns, and he draws balls and computes a histogram. But if I have a mixed signal, then I have this third guy who I call the mad caller, and his job in life is to mess things up. So the model for the mixed signal is as follows. At the first level, the mad caller is going to select one of these two guys. He won't tell you who. And after having selected one of these two guys, this guy in turn goes and selects an urn, draws a ball, conveys the information back to the fellow on top who calls out the frequencies. And then you construct the spectrogram of the numbers that he has called out. The point is that the total number of counts of a particular frequency that he calls out is going to have contributions from both speakers. He may call out F1 1,000 times. And this has got, of these, some number have come from this one and some from this one. And our job now is to infer how many of these counts came from the first model, first guy, and how many came from the second guy. Now,
quick question. I think you said this earlier, but for any given frame, you stop drawing when you reach the energy of the observation.
Yes. The total count is the total energy. There's actually a scaling factor involved, which in maximum likelihood solutions you can safely ignore. So now, this is the goal here. Now is to so what we have is the distribution of the numbers that have been finally called out. And what we would really like to do is to compute the distribution for each of these individual components. We assume that we have learned these erns from some training data. So what we really, all we really need to estimate are the mixture weights with which this person selected these erns. Yes?
Is it the same model as having all the erns together being just one person and estimating as you did before, and then just looking at what's the proportion that passes these red erns?
Yeah, absolutely. There is a certain advantage to actually looking at it from this two-level process, but if you ignore that advantage or you did not want to use it, what you say is absolutely right.
Is it the same exact model? Or
it will be the exact same model. There will be no difference. So now, what we really want to do is to compute the distributions for the two individuals based on the combined distribution. And based on that, because what you really have is a histogram, to compute the histograms for the two individual processes. And wonderful, we can use expectation maximization. As may I know your name?
Roman.
Well, so as Roman just pointed out, if I just throw all of these erns into a single group, right, and I have the final histogram.
But if you put all of it into a single group, then you're going to have only one. You're going to be sampled from only one core.
No, I'm just going to.
Each speaker could.
I don't need, no, what the point is, I don't need the second level at all. This person could be simply selecting erns.
Right. You need the speaker ID of the erns.
Yeah, we just need the speaker ID of the erns, that's all.
You need to use individual speakers'
Not
separate speech to train their model first
yes.
before you do that.
No, yes and no. In the cleanest solution, yes. In fact, Paris has some examples where he does this on runtime, where if the second speaker begins speaking after the first speaker has begun speaking, it doesn't take a lot of training data. So for the first 5 seconds, he can actually train bases from the first speaker, and then everything that remains goes to the second speaker. That's how we actually separated the piano versus the singer out. It does really well. So now, once you compute the mixture weights, given the erns and all these probabilities, you can say, okay, this is the sub-distribution that came from these erns. And that, in fact, is going to give you the spectrum for that speaker. And you can separate things out. If you actually look at the graphical model for this, you have the speaker, the mad guy, selecting the speaker, who selects an ern from which he selects a frequency. So the overall process for the generation of a spectrum of a frame is, first you have the mad guy selecting a frame, then you have the speaker selects an ern, and then selects a frequency from the ern.
Can I stop you here?
Yes.
So the speaker adaptive training, cluster adaptive training, they also have a very similar model like this, right? So it's a speaker dependent transformation or weighting based on some frequency model.
Correct.
And then that's how you create the speaker specific mixture model.
Correct.
So I'm trying to figure out how mathematically these two are different. So speaker adaptive training is mainly some mixture of the frequencies, and cluster adaptive training is, I think, after you do a transformation based on MLLR, you have a mean transformation.
Right. I find transforms. I'm sure one can find relationships. This is a very simple model, but many similar things. So, separation. You have nice simple formulae which give you mixture weights. Once you have the mixture weights, you can actually separate the signals out. I'm running over time, so I'm not going to play out the example, but it doesn't sound that great. Let me tell you. You typically get between 3 and 6 dB of enhancement of the desired speaker. In a best case, like the one that Paris showed you, where you have a nice resonant woman and a nice resonant man talking together, you can get up to 10 dB of improvement. In the worst case, when they sort of sound alike, you can get negative improvements for one of the speakers, where you're basically pushing signals from one speaker into the other. The competing C speaker is merely suppressed. They're not completely eliminated because of the nature of the model. And sometimes you get a few artifacts such as musical noise. But interestingly, in these procedures, you actually get fewer artifacts than the other masking-based procedures where you actually introduce holes. Now, the results, as I said, are not that great, 3 to 6 dB. Why? It's useful to look at the whole thing as simplexes. The spectrum for any speaker is a point within the simplex for the speaker. Now, suppose I have a mixed signal from two speakers. Let's say speaker 1 had 3 urns, the 3 blue dots, and speaker 2 also had 3 urns, the 3 red dots. The mixed signal is going to come from a combination of 6 urns. So although speaker 1 came from within this simplex and speaker 2 came from within this simplex, the mixed signal came from the larger simplex. And what we are really doing is to find out what the contributions of the various corners are to that point, and ignoring the contributions of the other speaker and reconstructing the spectrum based on only on the contributions of the target speaker. The problem is this region. Now, this red simplex extends all the way to these red points. The blue simplex extends all the way to the blue points. So any point that falls in this region could have belonged either to the red simplex or to the blue simplex. How are you going to figure out which speaker it went to? Or rather, in ball and urn terms, say if speaker A has an urn with a certain distribution of balls, and there are some combination of urns for speaker B which give you the same distribution as this urn for speaker A. And if I have some collection of balls from the urn for speaker A, I won't be able to say for certain whether it came from that urn for A or from that mixture of urns for B. And so what happens is the allocation of energies to the two speakers can be arbitrary, which really ruins things. Now, here's a hacky solution. We actually explicitly take into account the fact that there is this central part of urns which cannot be distinguished. And so instead of training 2 separate sets of urns, one for each speaker, you train 3 sets of urns. One is specific to the speaker, the second, one each is specific to each of the speakers, and then the central one is common to all speakers. And to generate the spectrum, speaker 1 could draw either from his urns or from the common urns. Speaker 2 could draw either from his urns or the common urns. And now when you get a mixed signal, you actually compute the mixture weights for all of the urns, including the common urns and the specific urns for the 2 speakers. And then ignore not only the urns for the other speaker, but also the urns for the common urns, because you really cannot be sure how they must be allocated. In fact, you can do slightly better than ignore them. You can redistribute the energy from those urns according to the proportions of the energies in the other urns. But anyway, if you do that, here is an example of what you get. Now this, I won't play the mixture. So wait a minute, it's a bit loud. So this is what I get using the regular thing. As I told you, the results are not always great. I'm trying to pull out the male guy, male speech, and it hasn't come out. But when I use the other process, you can see that the female speech is significantly reduced because, yeah.
So when you reproduce just the male speech, do you generate from the middle urn, or do you?
No, I don't. I just ignore it. I could actually redistribute all the energy from the middle urn based on the proportions of the energies in the 2 side urns, and that should in principle give us better. It does in some examples, it doesn't in other examples.
If you use the dynamics, you probably can get much better.
Yes, indeed, and I will mention that.
What stops you from defining a probability or prior probability on the simplex?
That's very quick. Okay, yes.
The picture you showed with the ambiguous region, that's if you have so you showed that in a 2D plane with 6 points, but here you're really in 1,000-dimensional plane, so there's no ambiguity. Is there?
There is, because you're going to get some regions of the simplex for speaker 1 will be almost perfectly explained by the simplex for speaker 2, and vice versa, regardless of the dimensionality. It's going to happen. They're not, because you're not, this is not an L2 space, it's scale. So anyway, prior information. there we go. What we actually have is a simplex for the speaker, and the sequence of spectra is actually forming a trajectory through it. Now, the points, every spectrum is one point in the simplex, but the points may not be uniformly distributed across the simplex. Some regions may be more populated, the others may be less populated, the third may not be populated at all. And we can take advantage of this. For example, in the same figure over here that I had earlier, if we know that this region is common to both simplexes, but speaker 1 favors this region, whereas speaker 2 really favors this region, then if a point falls here, it's perfectly okay to simply allocate it to speaker 1, because the probability that you will make an error is fairly small. So if you're willing to account for this sort of a prior, then instead of modeling the whole thing as a mixture multinomial, you actually model it as a Dirichlet-Polya process, where you have a prior Dirichlet distribution which decides how we are going to actually generate a point within the simplex. And then you have a second process which actually says how we are going to combine the corners, and then a third level which actually computes the histogram. The prior probability distribution for this distribution of points within the simplex we will assume is a Dirichlet. Here are some examples of what that might look like in a three-cornered simplex. This, for example, says that points are more likely to occur over here than over here. This says, all of these regions are more likely than this corner, and so on. And so now we will actually use a maximum a posteriori estimator, where we also use the Dirichlet prior in computing the mixture weights, the proportions to which the various corners must be combined to generate a mixed point. And then, of course, we do the same thing. We ignore the stuff that doesn't belong to the target speaker to reconstruct the signal. The formulae look a lot like what we had earlier. So this is the nice part of the whole framework, that no matter what you do, the formulae don't get more complicated. They all look fairly simple. Except that over here, when you use priors, you're going to get one magic number which tells you how much you're going to trust the prior over the data. And you get the second set, which is the Dirichlet parameter, which you have to learn from the training data. Again, I have an example here. Now, a single Dirichlet distribution only computes a single mode. It says that there is but one mode within the whole simplex. And this is not really a very good model, if you think of it. You still manage to get maybe half a dB or 1 dB improvement when you do this. It's not a lot. You get a minor improvement. Rather than show you the various examples, I'm going to show you that this is what I get using both the regular process. This is what I get when I use the Dirichlet priors. You can look at the spectra, and you can see that the spectra are in fact different. And I managed to successfully throw away a lot of the spectrum which belongs to the other speaker, and only play out the different signals to see what has been reduced.
Don't you had your dark really bright wash water all year?
So a lot of this is primarily the male speaker, which has been removed. So the signal has a lot more of the female speaker. You don't have to just model static distributions. You can actually model the whole trajectory using an HMM. Or you can actually use a mixture Dirichlet priors, and they would all help. The final topic, this is slightly off the trajectory that I've been following in the rest of the presentation. We'll talk about sparse representations. Now, in our model, the urns represent, yes?
The minimum zero norm?
Yes, but almost. We won't use a minimum zero norm notation here. We will actually use minimum entropy. Yes?
I don't know if you're familiar with that part of work, or if you're going to mention it at some point, the model that you're describing with Dirichlet prior, etc. It's also called in text latent Dirichlet allocator.
Yes, it's David Bly's work.
Yes. And the very nice thing about that is that it's been extended to using Dirichlet processes, and so
that's a wonderful. Okay, yes, and that
choosing the number of components that you have.
Perfect, and that is the wonderful part of the whole process, the whole formulation that we have, in that we just sit back and let the text guys do their work, and then we borrow the results and stick it in. So, and they do it.
In the same vein, in last year's NIPS, there's actually a paper which tracks the Dirichlet process as a trajectory in the simplex. So it also.
And the mathematics are all very straightforward. You don't need David Blay to work it out for you. It takes half a day to work it out end to end. right? So anyway, the sparse representations, our urns represent bases. Now, what we speak of when we want a sparse representation is that we want to explain each spectrum using the smallest number of bases. In ball and urn terms, we want to say that when the person is generating the spectrum for a particular frame, he may have 100 urns at his disposal, but for that frame, we want him to use the smallest number of urns. It's best if he uses only one urn and draws all of his balls from that one urn. That's the zero norm definition. Except there's a different way of looking at it, that we don't really need to think of it in terms of using the smallest number of urns. We have a mixture weight distribution over the urns, and we can say we want to minimize the entropy of this distribution, which gives you the same result. The significance is it forces each of the bases to represent as much spectral information as possible. If you don't enforce a sparseness constraint, then things can break up. I have an example here. So here I have three figures that are supposed to represent spectra. You might have one which looks like this, the other spectrum looks like this, and the third looks like this. And if I just train three bases, I could train these three bases, and I can use these bases, combine these bases to reconstruct these spectra with zero error. But the one thing that I need to use at least two bases to reconstruct any one spectrum. In fact, there are many unlimited number of solutions, unlimited number of ways in which I can get three bases, which can all be combined to give the spectrum with zero error. But there's no guarantee that any of these will make sense. Whereas if I use a sparseness constraint, then this is what I would get as the basis, because in the sparseness constraint I want to use the smallest number of bases to generate the spectrum. And if I do that, this is the only possible answer, meaning one of the bases has got to be this, the second has to be this, and the third has to be this. And now the difference here is that when you do this, each of the bases themselves carries a lot more spectral information. In terms of, yes?
Entropy mathematically equivalent to minimizing the zero norm?
It's not exactly the same, but they're related. This is a minimum entropy. You're sort of looking at it from a KL distance, right? And there is an L0, but they're related. Minimum entropy is much more tractable. Donna, who has like 200 papers trying to handle the L0 norm, and he hasn't gotten to the end of it. Whereas if you throw in an entropy term, it falls out.
Relax it with an L1 norm constraint, and then you can use stuff like
yes. And whereas if I use entropy, I don't have to do any of that. It just falls out.
Okay.
So here, to compute the spectrum for any given analysis frame, basically, I have a probability distribution over the urns, and then I have a probability of the frequency given the urn, and I'm combining all of these. Now, if I want to say that the representation must be sparse, then I want to say that the probability of an urn must be 0 for a large number of urns. That way, I'm using the smallest number of urns possible to compute the spectrum. Alternately, I can say that the probability distribution with which I'm picking the urns must have the smallest entropy. And you can actually formulate that all very nicely. This is the standard formulation that we use when we actually compute all parameters. This is a maximum likelihood formulation where we actually try to maximize the fit between the data and the model. Now, to minimize the entropy of our mixture weights, we just throw in an additional penalty within the same formulation. There's nothing. It's exactly the same, except there's a penalty term which says this must be minimized jointly with the maximization of the other objective function. And the arithmetic for this, fortunately, is textbook. It's all been worked out by Matthew Brand, so we don't really have to work very hard at it. But here are some results. This is on spectra. Now, I haven't used the log color maps, so the figures aren't as clear, but this is the basic spectrogram for a signal. I've computed. It appears even more washed out on the screen. This is the set of bases. The x-axis represents the basis index. The y-axis represents the frequency. And this represents the manner in which I've combined the bases. The x-axis represents time. The y-axis represents the basis index. So this y-axis and this x-axis are the same. And the more the number of dots over here in this picture, the more the number of bases I'm actually using to reconstruct the spectrogram. Now, if I do the same thing using a minimum entropy criterion, you'll find that this one is actually very sparse. You're not using the bases a whole lot. So you're getting a much sparser decomposition in terms of the bases. And correspondingly, although you can't make out, if you actually compare this basis figure to this, you would find that each of the bases here is much more spectrally rich than the bases up here. We can extend the whole minimum convolutive entropy learning approach to the convolutive versions of PLCA. There's just a result based on that. Now this is the figure that Paris showed, except this is just a, I think this is just the black, it's a grayscale version. And you have a collection of faces, and what we tried to estimate was one convolutive basis which must be repeated as many times as possible to reconstruct the whole figure. And when you do so, this is the average. It says that the figure is basically a repetition of this image. But when it tries to locate the figure, it's not very sure. Instead of giving you pinpoint, locations, it actually gives you these fuzzy blobs where it says, I think the face is somewhere in this region, and each spot has a different probability. Whereas if you actually use the minimum entropy version, each spot has almost a pinprick. It knows exactly where the face must go. So I don't have any audio examples for this. But generally, sparse representations derive much more complete bases. And this in particular is very useful because now it means we can actually learn, whether it be for audio or video, actual spectrally consistent segments which actually make sense. And so we can expect to get much better performance for both bandwidth expansion or speaker separation or any other decomposition based processing. So in conclusion, we've described various latent variable decomposition based techniques for analyzing audio and video data, and we've derived these from techniques normally applied for text analysis, which is great. We let the text guys do all the work and then we just take it. And there are several very promising avenues, and it actually remains work in progress. Thank you.